Let's now consider the case when the matrix A has complex eigenvalues. So assume that the eigenvalues has eigenvalues, say alpha plus I beta and alpha minus I beta. Then the eigenvectors, the corresponding eigenvector to, let's say, alpha plus I beta will be, let's say, vector A plus I vector B, where A and B are vectors with real numbers. So in this case, we say that one of solution is e to the alpha plus I beta times the vector A minus plus IB. And we can use the Euler's formula to write this E. So this is the same as e to the real part cosine beta t plus, it should be t, plus I sine beta t times A plus IB. Or we can open the brackets to see that this is in fact E alpha t A times cosine beta t minus B times sine beta t, this is the real part of this, plus I e to the alpha t A sine beta t plus B cosine beta t. So in fact we can choose to be our, so in this case we have to find two solutions, right? And we can choose to be our solutions this real part and this imaginary part. We can indeed check that these two are solutions of this system and prove that these two are linearly independent solutions. So let's do this. So let's prove that these two functions, two vector functions, are first of all linearly independent, and secondly, these are solutions of our given system. So recall that the alpha plus I beta was eigenvalue of A, and A plus IB is eigenvector. What does it mean? It means that if we apply A to the eigenvector, we obtain eigenvalue times this eigenvector, right? Let's now open this to see what we have. AA plus IAB, this is alpha A plus I alpha B plus I beta A minus beta B. And we can compare real parts and imaginary parts and see that AA in fact is alpha A minus beta B. And if we compare the imaginary parts, we see that AB is in fact alpha B plus beta A. So these things we will use. So the first step will show that x1 is solution of the system x prime is ax. So we will find x1 prime first. This will be alpha e to the alpha t cosine beta ta minus beta e to the alpha t sine beta ta minus alpha e to the alpha t sine beta tb and minus beta e to the alpha t cosine beta tb. Okay, let's rearrange these things as follows. We will look at cosines. So e to the alpha t cosine beta t, and in the brackets we'll have alpha a minus beta b, and also we rearrange the e to the alpha t sine beta t. We'll get beta a plus alpha b. And now, using star here, okay, let's write using, or it's not clear. Alpha a minus beta b. Alpha a minus beta b is exactly a. So e to the alpha t cosine beta t a minus e to the alpha t sine beta t, and this is exactly ab. Let's see what can be taken out the brackets. This is a e to the alpha t, and in the brackets we'll have cosine beta t a minus sine beta t b, and this is exactly the expression of x1, right? So this is ax1. So we started with x1 prime, and this is exactly ax1. So x1 is the solution. Similarly, you can prove that x2 is solution of the system. This will be your exercise. Check this by yourself. Okay, and what is left now to show that these two are linearly independent? So assume that x1 and x2 are linearly dependent. So we assume the contrary. In this case we have, it means that x1 is just some constant times x2, right? So let's write the value of x1. So x1 is e to the alpha t, let me open the brackets now, cosine beta t minus e to the alpha t sine, okay, I forget a here, and sine beta t b here. This is equal to c times e to the alpha t sine beta ta plus c e to the alpha t cosine beta t b. Let's again compare the coefficients in this case. So coefficient of cosine, we get that a is exactly cb, and coefficients of sine, we get that At the same time, minus b is exactly ca. So what do we have in this case? A is cb and b is minus ca, so this is c minus ca, which is minus c squared a. It means that if we move this to the right here, that 1 plus c squared a is 0 vector. This cannot be 0, right? So it means that a must be 0. And what was a? A was the real part of the eigenvector. Okay, this can be 0, that's fine. But since a is cb, we obtain that b is also 0. But u, which is a plus ib, is eigenvector, so cannot be 0. So we get contradiction. So the fact that we assumed is not possible. So x1 and x2 are linearly independent. Okay, great. Let's summarize. If, say, one of the eigenvalue of A eigenvalue of the matrix A is alpha plus I beta with corresponding eigenvector A plus IB, then the corresponding solutions linearly independent solutions of the system x prime is ax are x1 e to the alpha t cosine beta ta minus sine beta tb, and the second one is e to the alpha t sine beta ta plus cosine beta tb. So this is kind of a rule how we find the corresponding linearly independent solution in the case when we have complex eigenvalue. Let's now look at an example. So let's find the eigenvalues of this matrix. So the determinant, first of all, we need to find the determinant, which is minus 1 minus r, minus 3 minus r, and plus 2, which is r squared. How many r's we have here? 1 and 3 plus 4. And we have here plus 3 plus 2 is plus 5. So this is equal to 0. So the eigenvalues are the solutions of this equation. This is minus 4 plus minus square root of 16 minus 20 over 2. So this is minus 2 plus minus, here we get 4, minus 4 square root is 2, so just I here. So this is alpha, our alpha, and this one here is our beta. And we also need to find eigenvector. So we find the vector u So let's take the eigenvalue plus I. we need to find a vector u which will satisfy this thing here. So let's see what the matrix is. This is -1 plus 2 minus I, -1 to -3 plus 2 minus I. Apply to the vector, let's say the vector of x and y. This should be 0. So let's just calculate it. -1 plus 2 is 1 minus I, 2 minus 1. And here we have -1 minus I. Apply to x and y. Must be 0. So this will give us 1 minus I x plus 2 y is 0. And these two must be linearly dependent rows. So in fact only one row will give us the important information. So let's write y is 1 over 2 I minus 1 x. So let's take x to be, let's say, 2s, just get rid of this fraction to here. So the vector u then is x is 2s and y is I minus 1 times s. So let's split it into real and imaginary parts. So s times the real vector is 2 minus 1 and the imaginary vector is 0 here. There is no imaginary part in this component, and here we have just 1. So this will be our vector A. This will be our vector B. So let's write the general solution x1 of t, not general solution, but first let's write the linearly independent solutions. x1 of t e to the minus 2t, this is our alpha, and beta is 1, right? So cosine of t times the vector a, 2 minus 1. So is it indeed 2 minus 1? Yes, 2 minus 1 and 0, 1. Okay, minus sine the vector b, 0, 1. This is x1, and x2 now is e to the minus 2t sine t vector a plus cosine t vector b. So the general solution is the linear combination of these two. Just c1x x1 plus c2 x2.